Okay, so you almost certainly remember benzene from chemistry class, right? That classic hexagon shape. But what if we looked at it differently? What if I told you it's not just some random molecule, but maybe one of the most elegant pieces of code ever written? Not by a human, but by nature. That's the idea we're going to dig into.
And this right here, this is the whole idea in a nutshell. In coding, the best solution, the most elegant one, isn't about complexity. It's about solving a huge problem with a simple, powerful solution. And we're going to make the case that benzene's structure is exactly that. It's chemistry's ultimate hack, a way to get mind-blowing stability out of a design that seems almost too simple.
So, if we're going to call benzene elegant code, we kind of have to agree on what elegant even means, right? What's that secret sauce that makes a design, whether it's software or, a molecule, feel genuinely beautiful and smart? And I think this definition from computer scientist Paul Graham just nails it. An elegant design is succinct. It's about the power of a few things to do many. It's not about packing in more stuff. It's about getting the most out of the least. Maximum impact, minimum complexity. So let's keep that idea in mind, succinctness, as we look at the very first attempt to figure out benzene's structure, which you'll see was anything but succinct. Right, so think about any great piece of software. It never starts out perfect, does it? There's always a version 1.0, and it's usually kind of clunky. It works, maybe, but it's full of bugs and inefficiencies. Well, chemistry's first crack at modeling benzene was the ultimate version 1.0, a textbook case of some seriously buggy code. So this was the first draft, the Kekulé model. And hey, it got some of the basics right, like the 6-carbon ring. But look at the details. It suggested alternating single and double bonds. In coding terms, that's just messy. It's unbalanced. It implies that some of the connections in the ring are shorter and stronger than others. Structurally, that's just weird and awkward. And this is where the whole thing just crashes and burns. See, if that model with the double bonds was correct, benzene should have been super reactive. Like you mix it with something like bromine water and poof, it should react. But when they actually did the experiment, crickets, nothing. Benzene turned out to be shockingly stubbornly stable. So the model predicted one thing, and reality did the complete opposite. The code just wouldn't run. And that right there is what we call a model collapse. It's when the real-world data doesn't just disagree with your theory, it completely shatters it. In the coding world, it's that horrible moment you realize your whole approach is wrong. The first draft wasn't just a little buggy, it was broken from the ground up. Time to scrap it and start over. And this brings up a really interesting point about science and, well, learning in general. When we keep teaching a flawed model without explaining why it's flawed, we're basically just copying and pasting bad code. We're Xeroxing a lie. It's like trapping ourselves in a bug-filled loop that keeps us from ever finding the truly elegant solution. Okay, so version 1.0 crashed hard, but then came the rewrite. The elegant, refined solution that fixed everything. This is benzene, version 2.0, the elegant hack we've been talking about. So let's put them side by side. On the left, you've got the old Kekulé model, a mess of different bond links and separate double bonds. But look at the new model on the right. This introduces a totally game-changing idea, a single continuous ring of electrons shared by all the carbons. And just like that, everything clicks. All the bond links become identical. The molecule becomes incredibly stable. The prediction finally matches reality. The bug is officially squashed. And this maps perfectly onto our coding analogy, doesn't it? The clunky code had internal conflicts and buggy predictions. It was noisy and inefficient. But the clean code? It has zero internal conflict. It's perfectly stable. It's succinct and elegant. This is exactly what Paul Graham was talking about. So what's the actual hack here? It's this. Those 6 special electrons, the p electrons, they don't just sit still in one place. Nope. They are completely delocalized, which is just a fancy way of saying they are shared equally by all 6 carbon atoms at once. They're constantly circulating in this amazing strange loop above and below the ring. It's the perfect design for distributing stress, which makes the whole thing insanely stable and strong. But here's the best part. With great code, you don't just have to feel that it's better. You can prove it. You can run benchmarks, you can look at the data, and we can do the exact same thing here. We can actually measure the performance gain of benzene's elegant design. The proof, as they say, is in the numbers. Now, the way we do this is with something called enthalpy of hydrogenation. I know, it's a mouthful, but the idea is actually super simple.
It's basically a stress test for molecules. You measure how much energy is released when you break its bonds. Think of it this way. A really unstable, tense molecule is like a tightly coiled spring. When you break it, it releases a ton of energy. A super stable molecule, it's already relaxed, so it releases way less. Okay, so check out the results of our stress test. Based on that old clunky Kekulé model, we expected benzene to release a whole lot of energy, around 360 kilojoules. That's the tightly coiled spring. But when we actually measure it, the real benzene only releases about 208. That's a massive difference. It's not just a minor miscalculation, it's stone-cold proof that the old model was completely fundamentally wrong. And that gap, that 152 kilojoules per mole, that is the payoff. That's what we can call the stability dividend. It's the extra stability, the performance boost, that benzene gets from its elegant design. It's the hard data, the quantifiable proof, that this piece of molecular code is just brilliantly optimized. But, in science, just like in coding, solving one problem often opens up a whole new set of even more interesting questions. The story doesn't end with this perfect solution. In fact, benzene's clean code starts to get a new kind of bug report filed against it. And that leaves us with one last puzzle. For a molecule that's so stable and unreactive, when you finally force it to react, it does something really strange. Instead of letting an incoming attacker break its perfect ring structure, it just swaps out one of its hydrogen atoms. It does a substitution. It protects that elegant, stable core at all costs. So the question is, why? Why is this code so fiercely defensive of its own elegant design? Well, that's a question for another day. Thanks for diving into this with me.